So today's lecture is about bimodal experiments and actually also some software engineering. And for this, we need some literature. Again, John Ross always gives us some hints. You've seen it many times already, but today there are also a couple of new books that would be interesting if you're interested in the topic of data fusion and image fusion. I just see here now that this book here is actually published now, so I forgot to change that one. So that one you can also download if you like through ETH library, all of them actually. So maybe, yeah, this one should also be possible. We have already gone through a lot of different topics. We are getting close to the end of the lecture series. And we have been talking about images, how to enhance them if they are too noisy, understanding what the histogram means, segmentation methods, automatic, manual, semi-automatic. Then a next step after you have done segmentation, you may want to do the labeling of the objects to start getting more information, quantitative information about the object. And then we start analyzing the individual items. With that, most of the image processing part was already handled. So we created some statistics. And last week I was talking about dynamic experiments, a little bit about registration. And we also did some visualization. In the end, you want to present your results, and tables are usually not maybe the best thing to do it. So I also showed a little bit about plotting. Today's outline is about scientific goals of using bimodal imaging and the motivation for it. Then there is a new segment about section about segmentation. We already did a lot of segmentation already, and now I'm going to show yet another type of segmentation you can do when you have data from different modalities. And the last part is about software engineering, in particular with the aim to improve repeatability and reproducibility using your routines for yourself and for others. So we have until now only worked with single modalities. Now these images actually all offer neutron imaging, but it could as well have been X-ray images, ultrasound, MRI, whatever. But here are some challenges that I have come across, that we have problems with the segmentation accuracy, problems to estimate the water content, also classifying different materials or tissue in different items, objects, patients, because there are ambiguous overlapping distributions of each gray level. Another thing which is a problem is if you want to do something where the object changes the shape throughout the experiment, you have to do something to be sure that it's changing. What you are seeing is due to the change introduced by a process, or what you see is introduced by a shape change of the object. And if you have a single gray level, it's very difficult to determine this. Then we also have, for material science, one is penetration power. So how suited is the method, the modality you have chosen for actually see through the objects you want to see through? That can also give you ambiguous readings. And well, there's a lot of challenges within this different single modality experiments. So reasons to select a specific imaging modality is, first of all, you need good transmission, good contrast. The relevant features should ideally be visible, otherwise it doesn't make sense. And different materials can also be identified. What would talk against a specific modality is that the transmission is pretty bad. So for example, if you have a lot of water in a sample, more than say 10 millimeters, then you can't see through it with neutrons. With X-rays, water is no problem. In the reverse, you can say that, well, you want to see through 2 centimeters of lead. And most of you realize pretty quick that X-rays is not a good idea for that, but neutrons would be. So then you have to really choose the modality that actually suits your purpose in the experiment. Other reasons not to choose modality is that not all features are visible, or you can have almost the same gray level for 2 things that you want to separate. That also makes it difficult to separate them. And this is when you look at a single modality. Now we want to really see the things. So the question is, can we find a modality that actually does what we want? Or do we need to do something else? And the aim of multimodality is to match all the advantages of each method. You can see, for example, some items in one modality, you can see other items in another modality. And in the end, you want to see both of them. And you don't want to have the disadvantages. And ideally, you should be able to separate, to see everything you want, and you want to also suppress all the artifacts or omitted information that you don't see. So ideally, you want to extend the range of operation for your experiment. Maybe also extend spatial or temporal coverage. So one modality may have extremely high resolution, but it only provides you a little bit of information, and that can be useful then when you impose it on the other one. Also the temporal coverage, that you can say that one method can acquire extremely fast, but maybe you want in between, you want still information from the other modality, and then you can, with the help of mixing the 2 of them, you can actually bring out more information from the data. This will hopefully reduce uncertainties, increase the reliability of the experiment, and that in the end will give you a more robust overall system performance. A little bit of playing with that. For those of you who have seen National Treasure with Nicolas Cage, he used some kind of multispectral glasses to see different text on a document. Well, that was just a little bit of playing, but the idea is still there, that with the help of different filters or different modalities, you can actually extract more information than you see with the bare eye. And when you start doing an experiment, an imaging experiment, there are actually four components that you have to match and make sure that they work together. One is you have your application. That is the thing that you know pretty well, hopefully, because that is the base for your experiment. Then this probably has a physical component, so you need to have some physical understanding about what it is you're looking at. That combined with the acquisition, you have to make sure that the acquisition can resolve what you want to see with the right contrast, in the right time, frame rate, etc., etc. And in the end, in order to get the information you want about your specimen that you observe, you also need to have a reliable processing chain to get through the system and get your quantitative data out. So let's look at combinations of different modalities. And the one I myself have been working a lot with is neutrons combined with X-rays. And here you can see two radiographs, one using neutrons and one using X-rays. And you can see that many metal things are very transparent with neutrons, but the plastic components, they are pretty dark. On the other hand, you can see for the X-rays that the metal is very dark and the plastic is transparent. So you can see here that there is a complementarity between the two modalities, which we hope to be able to gain more information from. The periodic tables you see below, there I have put shadings depending on the attenuation coefficients. And you can see with the X-rays, it's a pretty linear scale, more or less, with, or at least a continuous scale for more height set, from low set to height set elements. With neutrons, it's pretty jumpy, and you can have some extremes that hydrogen, the lightest element, it has a very high contrast, whereas lead, that you know from X-rays, is very black, opaque. That is very transparent with neutrons. So you can see here, if you choose the right combinations of elements, this would be a very good match. Not always, but there are cases when you can really get more information out of it. Typically in porous media experiments, this is a great thing, where you can see the soil, for example, pretty good with the X-rays, and you can see the water really clearly with the neutrons. So that is a very good combination. If you go for medical imaging, then we have the normal X-ray tomography combined with MRI, and you can do some fusion to get more information. So you get the very sharp edges from the bones using the X-rays, and you get more functional information or more tissue information from the MRI. Then we can also combine the MRI with PET scans and fuse that information. And SPECT, so you can get the functional imaging combined with tissue imaging. And that's a very strong case, actually, because many, so PET and SPECT, as you can see, are relatively low resolving methods. But then if you impose it on a high resolving image, it still provides you very good information about what's happening. So these are some examples that are used in medical imaging. Then another that's actually using the same radiation technique or radiation type, but using grating interferometry, you can you observe the beam as you see the beam as a wave instead of a particle cloud that is moving forward. And with that, you can extract differential phase contrast or phase contrast. And you can also extract dark field contrast. And the dark field is related to ultra small angle scattering of tiny items in the object. And those would also be a thing that you could combine into gaining more information about the objects. And then is the question about putting more physical interpretation in what you see, and give that the motivation to how to fuse these informations. This is something some people have started doing. I actually didn't dig up a reference, but I think in the Tomcat group, they have done some fusion experiments with grating interferometry. Another one, again, is not fully multimodal, but it's multispectral imaging. Is also what I have shown already in when we talked about principal component analysis. But this could also be a thing you can see as bimodal. For example, if you look at polycrystalline material, you can look at images taken at about 3 angstrom and at 4.5 angstrom, and then you have a very good contrast. And depending on the crystalline type, a crystalline arrangement in the ion crystals, you can get different contrasts within the object. So that would also be something where you can use the multi or bimodal approaches. Then you don't necessarily have to just talk about images, but you can also look at different dimensions of information. So you can have single point measurements, like temperature, humidity measurements combined with the image data and merge that together, or fuse this information together. Can also have some surface information, surface roughness, surface temperature again. And you could also compare single radiographs with tomography data. Sometimes you want to, for example, in medical imaging, you don't want to expose the patient to a CT scan as soon as you want to see something, because that's a lot of dose that the patient gets doing that. So if you can combine the CT information with single radiographs, then you can also get maybe the intermediate information during a treatment with less radiation dose, and that fusion would also be pretty beneficial. So it doesn't have to be that you combine always images of sometimes exactly the same size or images of maybe different sizes together, but it can also be other dimensions. So I have already mentioned the words fusion, and that's a terminology that is being used in literature. Data fusion, image fusion. So it's in principle an umbrella terminology for the theory and the techniques and tools that are used to combine information from different sensors or data derived from different sensors, and bring them together in a common platform and represent them together too. And the aim of doing this is actually to improve the quality and of the information you get, so that it, in some sense, or in the sense that is relevant to you, provides you more information together than each source is providing individually. And there are a lot of fusion approaches, and I would also say that there is no golden recipe saying that this is the way we fuse. It's like with all experiments, you have to tailor your analysis and fusion approach depending on what it is you want to look at. So I have listed some variations here. So you have the multivariate fusion. So all data are combined with the same scales, the same concept. So you work with them together, completely merged together. Then there is augmented fusion. So you can use one modality for one purpose and the other modality for another purpose. So you can, for example, use one to segment structures in the image, and the other one to observe a process that's going on. And then you can use the structures that you have segmented using the first modality to see where things actually are happening. And another one is artifacts reduction by fusion. So, for example, in tomography, you have often starvation artifacts, for example, from metal implants in medical imaging. They are always very annoying for the analysis. And if you can have a second modality, then you can close in closer around these metal implants. And there are some approaches that you do even during the CT reconstruction, take the information from one modality and use that as guide for the second modality. Of course, single approach may be good, but often you have to combine all these until you get the final result. And which strategy you choose depends more or less on your experiment. So what is sample composition? What are the objectives of your experiment? And of course, also the condition of the data. What do you need to do in order to get the data in the right concept that you want? Then a little bit more abstract levels of fusion. You can have different combinations. So you can have data to data. So in principle, you are in the same scale still. You have the same images, or you have two images and out comes one or two other images which are fused in some way or improved in some way. But you can also already have image and produced labeled regions based on the images. Then you can go a higher level of abstraction, that you have different features that you find in each modality, and those you fuse into new features. Next level is you bring up all these features from the modalities or features that you have extracted, and then you want to get a decision based on all these features you have extracted. And finally, you have decision to decision fusion, and that could be that you have several classification methods and already decided what they are, and then in the end you fuse the output. And one example is, for example, is the random forest that we mentioned already a couple of lectures ago. So there are different levels that you can select, and depending on what you want to do, you possibly can actually do it on different levels, but these are the abstract combinations that you can extract. Our typical workflow is when you do image fusion is first you have, of course, image acquisition. You get images, maybe different shapes, different scales, everything. Also different views of the sample. And then you need to do some registration. So aligning the images with each other. Next step is to do, or you could do then pixel fusion, pixel to pixel comparisons, or you can go one step higher, that you do feature fusion, that you have already labeled regions and you want to compare those. And finally, then you have this decision fusion. And after that, when you have the fused data, then you can start doing different statistics or modeling, or you can also go towards the presentation and display of your data. Then there is a term also defined as catastrophic fusion, and that's something you should avoid and be very critical to not just saying I'm doing multimodal, I'm fantastic, but the idea of catastrophic fusion is that the combination of your different modalities actually perform worse than the two modalities individually. So it could be that you select the wrong variables or have a too complex combination, or actually that the sensor information is canceling each other. Or maybe they are really linearly correlated, so there is no point in combining them. So there are pretty many reasons. So if you start going for the bimodal imaging, then you should also be aware of what it is you're actually looking at. But usually when you have done the selection of variables, you usually already have a pretty good idea why you're doing it. So, but anyway, I just want to mention that this can also happen. A registration, actually, I already talked about last week, so I'm not going to spend too many words about that. But in principle, what you're doing is you have one fixed image and one that is moving towards the fixed, and maybe you have to flip them, and then you have to rotate them in order to get them on the same orientation, position, and scale. So that would be the process that you have to go through. When you do the registration, a little bit some practical considerations. So it is in general optimization problem, and you have usually many local minima in this problem. So what you can do is do manual or guided registration. And then you can do, well, you can do the whole registration manually, but I wouldn't recommend that completely. You can also identify landmarks or points, lines, planes in the data, which the algorithm should work to align up. What is often happening is people are doing coarse pre-registration manually, just to tell this is the place where I want to start. And then it's relatively quick for the algorithm to find the right matching. And then afterwards, we have an iterative process where we can use different metrics, which I mentioned last week. And one problem is actually when you do multimodality registration is that some landmarks vanish in one modality, so you can't use them easily. In one, it's clear that you have stones spread out over the image, but the same stones, they are more or less fused with or merged with the background, so you don't see them. One thing that is done is that you can introduce fiducial points, so you more or less just glue some dots on the object, which helps you to guide the registration process. So that's actually one thing that you could do already during the experiment. Let's go for the first more or less manual or qualitative fusion. So what is done a lot is, as a first step, is registration and covisualization. And that is well supported with software, commercial or open source, like VG Studio, Aviso, etc., or 3D Slicer, which is an open source software. With those, you can register the data sets, and you can also do this in an interactive process. And you can also do the segmentation interactively in order to get nice results. This is a sword that was found in Lake Zug. And we did it actually in our beamlines, where we could see that, and the combination is very nasty actually for both modalities. So the combination is that we have iron, we have corrosion, we have wood, we have amalgam with mercury in it. And some of these components, they were very good with one modality, and they were really ruined the other modality, and reverse. But in the end, through the fusion, we could get a very nice reconstruction out of this data set. So if you want to read more about this, you can, oh, actually, I don't think I put the full reference here, but if you're interested, just send me a message and I can give you the reference. There are even some YouTube or reportings in what was it, Einstein program in the television. So there is, the whole story is documented both as publication and in TV. So let's look at what we can do with the visualization. So here I just took a little example, test sample that I started when that I did when I started working with neutrons and X-rays together. And here you can see slices of the two. And this is just visualizing the 3D shape of this snail shell. And one visualization technique that is very helpful, at least during the registration, is to use a checkerboard visualization. And the idea of this is that you have this checkerboard and you interleaved put modality A and modality B, A, B, and so on. And then you can see how well the two modalities are fitting with each other. Here is some code that I wrote to produce this. So if you want to do this kind of mixing, it's you can just take this function here and call it like I do on the next slide. The code is actually hidden in the notebook, but if you open the notebook, you can see it. So here we have the neutron image and we have the X-ray image. And then if you combine them, you can see here how well, how it is, the registration has worked. And you can also see the contrast between the two objects. And this is a pretty helpful way of visualizing during the registration process as a quality feedback mostly. But sometimes you can also use this even in the publication just to as qualitative demonstration of what the different modalities actually show. Another one is to work with color channel mixing, where you take the different color channels, RGB, or you can also use other color models, but RGB is pretty straightforward to use. So you put the images of one modality in for red, one for green, and then the last channel, you take the average of the two modalities, so you get some average intensity. And then depending on which order you look at them, so here I took image A as red and image B as green. Here I took A as blue and B as green. And here I took red and blue. So depending on what you want to show, this one looks very acidic, this kind of visualization, but it's very common that people use this one because it's the first two channels. But with a little bit more thinking, you can use more smarter combinations. So for example, this combination is very useful if you're looking at water in soil, because it turns out that the soil is more brown, yellowish, and the water turns out blue, which is perfect. So be a little bit creative when you choose the channels if you would like to do this kind of visualization. This is also very popular to do, actually. Then we switch over to the segmentation task, which is actually going towards more quantitative work. And if we look at the histogram of a single modality, you have two classes in it. And as you can see, if you look at the yellow line, which is the total histogram, you can see that it's very hard to get some decent segmentation from this. Of course, you can say that in the middle, we have the threshold, and that should be good-ish. No, the whole blue area here is actually a very ambiguous area for the decision. And that's not really good because you will get a lot of misclassified pixels. Some are right, but some are also not right. Well, in some cases, as you have seen, you can do opening and closing operations and get rid of the worst. But if the overlap is this big, you should do something. At least apply some filter in order to separate the classes a little bit more. Now, if we add the second modality here, please note that I have the blue class here and the red class here. So the red class here brings higher transmission than the blue class. In the second modality, on the other hand, you can see that the red class has less transmission than the blue class. So it's actually flipped, but still, it's the same ugly histograms. So the next step is then to bring it into the bivariate histogram, and all of a sudden you have a great class separability between the two classes like this. And this is something that is very is used much now in the combined neutron and X-ray imaging experiments. Now a few facilities worldwide. So to my knowledge right now, we have 3 combined beamlines worldwide. So let's look at the real image. Here I have roots in soil, And you can see in the neutron image, you clearly or very nicely see the roots. But you would expect that there is some kind of hole at this place. But if you look at the X-ray image, you can see that this hole is definitely not a hole. It's probably some kind of stone. On the other hand, the root canal appears here as void, because the root is mainly water, and compared to the higher density materials in the soil, it appears just as a void. So if we look at the bivariate histogram of this root slice, you can see that we have some, well, the histograms, they are pretty merged. You see some bumps, but you probably wouldn't do a good segmentation based on this. Here, you can see also that I've used a logarithm of counts, because otherwise you would only see the background peak or that peak. So that's background and that's the soil. And then what we are looking for is actually one of these two peaks. This is the container and this is the root data. And this is what we now want to segment. And if you think back, you already may have some ideas about methods you can use for the segmentation. And what we want to do is, first of all, we have our images, which are registered and hopefully also corrected for artifacts. And then we want to divide them into different classes. And one way would be to do it through hypothesis testing. So you say you have a distribution for each probability distribution for each class, where you have some average value and a covariance matrix, and that for each class. If you want to go into classification theory using statistical methods, this is kind of a central reference used for that topic. Pretty good written, actually. What methods we have used before to do this have been k-means, k-nearest neighbor, some regression techniques, or neural networks, actually convolutional neural networks and UNets, etc. And now I'm going to introduce yet another model, which I haven't mentioned until now, which is the Gaussian mixture model. And here we assume that the data each class has a Gaussian distribution between the two variables. So it's not sure that it's just a nice Gaussian bell, but it can be a little bit rotated, and the rotation is described in the covariance matrix. And then there is a mixing coefficient also in this model. And if we produce some spots in the, so this is just a synthetic data now, some from two Gaussian distributions, you can see that one is slanted in this way and one is, oh, yeah, it's generally slanted in that way, and that one is in the other way. And using the Gaussian mixture model fitting, you have tools already in scikit-learn that can extract you Gaussian mixture models and fit the data. You just say how many components you want to fit, and then it provides it for you. And afterwards, we can do predictions based on this. And you can see here that if we have only one class, well, of course, it places it here on the center of the data. But with two classes, it already looks pretty good. And then you can see that one is actually slanted in this way, the other one is slanted in that way. If you add more and more classes, of course, there will be over segmentation, which is a problem we also had, for example, when we looked at k-means or k-nearest neighbors. Of course, you will get the fitting machine will try to fit what you want, the number of classes you want to have, and it does it best possible. So it's not always, so you have to be aware of how many classes you select. Then when you start doing the actual segmentation, you have your point in the data, you have some value from modality A and some value from modality B. And then you compare different distances between the point you have measured and the points, the centroids, or the statistical information from each of the classes. Euclidean distance is pretty straightforward. You just take the centroid of each Gaussian and compute the distance, and you choose the one that is closest. So it's a kind of a nearest neighbor comparison. Then we have Mahalanobis distance. Then you include the covariance matrix of the class in your decision, and that gives you a better precision in the distance calculation. And finally, this is kind of the big gun, is the Bhattacharya distance, where you combine, you have to actually have a covariance matrix of your local information as well as of each class. And to graphically illustrate this, you have the Euclidean distance, where you just measure the distance from the point you have measured to the centroids of each class. Then you have, actually it could be that you are saying that it belongs to this class, but it would rather belong to the other class. So you have greater ambiguity when you use the Euclidean distance. With the Mahalanobis distance, you already include the shape of the distribution of each class. And then you can see it's much easier to say that this dot is more likely to belong to this class. And finally, with the Bhattacharya distance, you have again the class shape, the Gaussian bells of each of the classes. But then in addition, you also measure the covariance matrix, and then you have a even more detailed decision. It's more complicated to compute, and you're probably, you will have to compute more information about the image. So I would say this is probably the more relevant way to select the classes of each item you look at. Here I did an example using the Euclidean distance in the root image, and here I have my classes marked up, and you can see that the Euclidean distance puts essentially a line between these classes here, and the segmentation is honestly not so convincing, because you can see here the roots have been classified as the container, and also here some roots that are given the container class. And the reason is they are very close to each other, and in the X-ray data I had a little bit too much copying caused by beam hardening. So in order to make this work well, you need to really look into having flat images or correct for it in some way. But you could also even add in more information about positions, like you add, like we did also with K means, that you add on a position grid, but still roots touching the container, they are tricky. And another way, this is more, say, speculative. It's not a very easy task to do, but you can actually look into Beer-Lambert's law and try to solve equation systems to extract the density or sizes of different objects. And the idea then would be that you have your set up the Beer-Lambert's law for neutrons and X-rays, for example, getting the result out, and then you try to solve for example, the density, the local density in the images. This requires really exact flat images, otherwise it will not work. So I actually haven't tried it fully, but it's something that is worth at least have a thought about. And if we go one step further, last week we talked about time series, and now we go into multimodal experiments, and often bimodal experiments are done separately. You have a scanner for that modality, and 2 rooms away or 2 buildings away, you have the other modality. And that is a problem for some experiments where you want to see things at the same time. So the next step is going towards dynamic experiments and having combined setups. And the setup that we have now at our beamlines at PSI is that we have the neutron beam going through in this way, and then 90 degrees across the beam, we have an X-ray beam, a cone beam. So we can actually do simultaneously acquisitions of both X-rays and neutrons. And with that, we can follow, for example, how a waterfront is moving through a porous medium, which has a relatively high clay content, which means that when water comes into it, it starts swelling. And the swelling makes the decision very ambiguous. Is now my intensity change caused by water addition, or is it because the shape has changed? And that can be captured in this kind of setup. And this brings me to the end of the first part. And let's take some minutes break.